The 1,000-year blackout. Why Earth's magnetic shield is failing. The first warning doesn't come from a siren. It comes from silence. An entire satellite camera goes blind as it crosses the South Atlantic. Alarms cascade, memory flips bits, and a space station slips to safe mode again. Down here, grid operators hear transformers hum on a clear day. Nothing exploded. The shield just thinned. Earth's magnetic field is weakening faster than anyone expected. That means your plane, your grid, your GPS timing, your cloud backups. Vulnerable. Strange blobs near the core are meddling with the field. To understand the blackout risk, we're going underground, way underground, and into the one corridor satellite's dread crossing. Roadmap of revelations. Here's where we're going and why you'll want to stay. First, the South Atlantic Anomaly, space's Bermuda Triangle, isn't just growing. By 2024 to 2025, it's clearly split into two lobes, one over the South Atlantic, another southwest of Africa. That bifurcation doubles the danger zones and gives us a live diagnostic on the core. We'll hear how operators plan around it and how it still bites. Then we step out of orbit and into rocks that remember. Lava flows, seafloor stripes, tree rings, and tiny crystals hold receipts from past collapses. They show that the field doesn't fail politely. It slumps regionally, fast, and sometimes flirts with reversal. The La Champ excursion around 41,000 years ago, also framed as the Atoms event, saw shielding plunge and atmospheric chemistry shift. Some researchers even link its timing to Neanderthal decline. Others disagree. We'll flag what's firm and what's debated. Now, the deep suspects, two continent-scale structures at the core-mantle boundary called LLSVPs, or Blobs under Africa and the Pacific. The newest models treat them as active players, heat hackers, that redistribute heat flow, nudging the geodynamo into weak patches and local reversals, exactly where the South Atlantic keeps acting up. Then the engine itself. The liquid iron outer core runs a twitchy dynamo. Change boundary conditions a little, and the field reorganizes a lot. You can see that sensitivity in real time. The North Magnetic Pole sprinted towards Siberia at roughly 55 kilometers per year in recent decades, forcing navigators to update models faster. Finally, we put it all together. Blobs plus Dynamo equals a tidy dipole turning multipolar. Bad news for satellites, GNSS timing, power grids, and aviation. We'll test those systems against real storms and map what fails first. Along the way, we'll keep it human. Pilots, line workers, mission planners, because stakes only matter when you feel them. Let's start where satellites go to die. The South Atlantic Anomaly, the Bermuda Triangle of space. If Earth's magnetosphere is a battered umbrella, the South Atlantic Anomaly is the ripped seam where rain drives straight through. For decades, operators have watched instruments glitch over a swath from Brazil across the South Atlantic towards southern Africa. It's routine enough to have its own checklist: SAA crossing, power down sensitive detectors, scrub memory, hope watchdogs don't cascade into a full reboot. Radiation belts usually sit high, corralled by the global field. Over the SAA, the inner belt dips closer to typical satellite altitudes. Spacecraft that cruise through low Earth orbit, medium Earth orbit, even some higher passes, get peppered by energetic particles that flip bits, burn pixels, and age components early. Hubble used to take naps there. Its experiments ride it out. CubeSats? They roll the dice because mass is money. This isn't folklore. It's in the logs. Star trackers lose the sky. Particle counters peg red. CCDs bloom with phantom hits. Many missions shut instruments off over the corridor to save their eyes and brains. Others accept data gaps and call it survival. Airlines and nav providers don't melt at 35,000 feet. The atmosphere still shields, but precision timing rides on satellites whose health erodes faster in this corridor. Insurers read dose histories and tweak premiums. Quietly, routes and maintenance windows shift. Here's the shift that changed voices in control rooms. The anomaly isn't just broader and weaker, it's splitting. Using 11 years of ESA swarm data, researchers report that by 2024 to 2025, the SAA shows two clear minima. One anchored over the South Atlantic, another southwest of Africa. That bifurcation doubles dodge zones and complicates prediction. For core scientists, the geometry is a clue. Why here? Weak field means less bending of charged particles, so they dive deeper. A crustal cause can't explain the scale or the change rate. The fingerprints point deeper, to the core-mantle boundary, where heat escaping the core drives the dynamo. Their seismic tomography maps one of the Blobs, the African large, low shear velocity province, sitting beneath the Anomalies footprint. Whether it's hotter, compositionally different, partially molten, or all. 3. It changes how heat leaves the core. Uneven heat flux reroutes convection in the outer core. Change the flow, change the field. Recent models sharpen that. Heterogeneous heat flux at the boundary seeds, weak spots, and even reverse flux patches. The African LLSVP's footprint aligns with the long-lived South Atlantic sore spot. It's not proof, but it's a straight line from surface pane to deep structure. And the details matter. Since the early 2020s, the lobe southwest of Africa has weakened faster than the Atlantic lobe. That acceleration trims satellite lifetimes on certain arcs and hints at active forcing along the African blob's complicated rim. On the ISS, safe modes and experiment pauses over SAA passes aren't drama, they're normal. Instruments that chase faint cosmic signals sit useless, while radiation hammers through the weakened shield. Earth observation missions that need continuous coverage live with holes in their maps. There's a quieter, costlier impact. Software. Error-correcting memory saves you until it doesn't. Single event upsets are random, but their statistics skew ugly in the corridor. Flip the wrong bit in a power controller at the wrong microsecond, and you get an unexpected reboot, or a stuck actuator. Operators test for this. New processors and power schemes still bring new unknowns. Every mitigation is a trade. Heavier shielding means less payload. Avoidance burns fuel. Accepting data gaps means science you never do. Add the human layer. A flight across the corridor on a quiet solar day is uneventful. On an active day, the anomaly is a soft spot. Ground monitors watch for induced currents in long lines. Dispatchers reroute polar flights for radiation dose. Down south, the SAA makes space weather feel closer to the ground. Now connect the dots. The bifurcation that showed up clearly by 2024 to 2025 isn't a surface quirk. It's a fingerprint of changing flows below, likely shaped by that African blob's heat hacking of the core's boundary. Meanwhile, satellites track other tells: westward drifting flux jets under the equatorial Atlantic, and a north magnetic pole sprinting towards Siberia at about 55 kilometers per year in recent decades. Signs the Dynamo is in a twitchy mood. Here's the tease that pulls us deeper. If the sky is acting weird, the rocks below kept the receipts. Lava flows, baked clays, and tree rings have logged this corridor's bad behavior before. The South Atlantic has been a repeat weak spot across millennia, and the deep structure under Africa keeps showing up as the accomplice. To test whether today's split is a prelude to a longer slump, or just a noisy chapter, we have to read those ancient postcards from the core and meet the blob shaping the boundary heat map. The Dynamo feels every second. Rocks that remember. Ancient magnetism tells on the core. To understand why today's shield is thinning, we go quiet, into cooled lava. When a lava flow hardens, iron-bearing crystals align with the magnetic field and lock it in. It's a postcard from the core, mailed in basalt. Stack enough postcards across continents and ages, and you can watch the field twitch, stall, and sometimes trip over itself. The seafloor keeps a second diary. At mid-ocean ridges, magma freezes into stripes of magnetization that mirror the field's flips through time. Sail a magnetometer across the Atlantic, and you'll read zebra bands. Normal, reversed, normal again. That barcode tells us reversals aren't rare in deep time, but the surprises live in the speed of local change. Zoom from millions of years to thousands. Tiny single-domain grains in baked clays and volcanic ash, basically nature's nanoscale compasses. Record intensity as well as direction. When those grains are dated precisely, they show episodes where field strength plunged within centuries. That kind of stumble is an excursion. The dipole weakens, local reversals pop up, then the global field snaps back. The headline act is the Lashamp excursion about 41,000 years ago. The field's dipole collapsed to a small fraction of modern strength. Proxies and ice cores in tree rings, like beryllium, tin, and radiocarbon, spike as cosmic rays surge through a shrunken shield. Auroras likely wandered far from the poles. The atom's event framing goes further. Combine that slump with solar mood swings and you get ozone loss and atmospheric shifts. Some researchers argue the timing overlaps stress in ecosystems and even Neanderthal decline. Others push back. Correlation isn't causation, and climate is noisy. The firm ground is this. When the dipole slumps to Lachamp levels, radiation climbs, auroral ovals expand, and the upper atmosphere's chemistry moves. What makes Lachamp matter for us isn't only the sky show, it's the pattern on the planet. Paleomagnetic maps don't smear weakness evenly. Certain longitudes keep showing trouble across multiple excursions, especially those tied to Africa. That persistence is hard to explain with a purely chaotic core. It hints at a boundary nudge. Something in the mantle biasing the flow into repeatable patterns. Look at younger records and you see the same asymmetry. Archaeomagnetic data from fired pottery and slag in the Levant reveal a multi-century intensity high, the Levantine Iron Age Anomaly, while the South Atlantic trends weak. Global reconstructions over the last 3 millennia show non-dipole features pulsing and drifting, but they cluster. The South Atlantic soft patch, the same one hammering satellites today, has a history. Meanwhile, some lava sequences capture eye-blink swings, directions whipped by tens of degrees between layers laid down years apart. That says the outer core can reorganize fast. You don't need a full reversal to cause trouble. A regional collapse can arrive on human time. Now tie the rocks to the blobs. When modelers bake a lumpy heat map into Dynamo simulations, hotter here, cooler there, the weak and reversed flux patches tend to nucleate above hotter, anomalous regions at the core-mantle boundary. The African LLSVP sits beneath the South Atlantic's long-lived sore spot. It's not a perfect match in space or time, and it doesn't prove cause. But lava directions, archaeomagnetic intensity highs and lows, cosmogenic isotope spikes, and today's satellite maps point the same way. Deep structure is steering the game. One more detail the rocks whisper. Reversals aren't clean flips of a giant bar magnet. The dipole fragments into multiple poles that wander. At ground level, that means a compass can point differently 1,000 kilometers apart, and shielding becomes patchy. You don't need the entire planet to go weak before systems notice. Regional windows open first. There's also the tempo. Secular variation, long-term drift, shows a westward march of features, the same bias satellites see today under the equatorial Atlantic. In the rock record, that drift leaves directional paths that arc consistently, adding another clue that deep jets and boundary lumps have been in dialogue for a very long time. In the South Atlantic, it's a repeat offender. From Holocene clays to Iron Age kilns to Pleistocene lavas, reconstructions keep finding a weaker-than-average corridor in that neighborhood. That history doesn't doom us to a flip. It does say the current bifurcation is part of a longer habit, likely fed by uneven heat leaking through the African blob's footprint. So the receipts are clear. The field can fall hard and fast regionally. The South Atlantic has been a habitual weak zone, and colossal structures at the core's edge keep showing up at the scene. The rocks don't tell us everything, but they narrow the suspects and set our next move. Follow the heat to the bottom of the mantle and meet the blobs that might be hacking the dynamo from above. Meet the blobs, LLSVPs, at the edge of the core. Follow the weak field down and you hit a coastline in the dark. The core-mantle boundary, 2,900 kilometers deep. That's where earthquakes turn into X-rays. Their waves slow and bend through 2 colossal regions that don't behave like the rest of the lowermost mantle. Geophysicists name them large, low, shear velocity provinces. Everyone else calls them blobs. One sits under Africa, the other under the Pacific. Each sprawls thousands of kilometers with edges so sharp they look like cliffs and vertical relief close to 1,000 kilometers. They aren't smooth balloons. They billow, bulge, and throw odd shadows on every seismic map we've drawn. We know they're real because the travel times don't lie. Shear waves crawl inside them compared to the surrounding rock. That could mean hotter material, different chemistry, partial melt, or some mix. At their rims, some studies pick up ultra-low velocity zones. Thin, pancake-like patches where waves nearly stall. ULVZs might be iron-rich melt, or just rock packed with metallic components. Either way, they change how heat leaks out of the core right beneath them. That's the lever that matters for a magnetic field born in moving liquid metal. What are the blobs made of? The argument runs hot. One camp says they're mostly thermal. Huge, warm piles ponding at the base of the mantle, too dense to rise, too buoyant to sink. Another says chemistry rules. Recycled oceanic crust that subducted long ago, or primordial reservoirs, ancient stuff from Earth's formation that never fully mixed. It doesn't have to be either, or. If you enrich rock with iron and keep it hotter, you raise density and change sound speeds. Dense things slide down. At the base, there's nowhere to go but sideways. So they spread out, build plateaus, and develop steep slopes at their edges. Those edges act like factories. Mantle plumes, hot, buoyant columns that feed volcano chains like Hawaii, often trace back to blob rims. If the rims are hot and chemically distinct, they'll spawn more plumes. That tells us the blobs aren't passive. Heat is flowing through and around them. The distribution isn't uniform, and the core. Beneath feels every patch and puddle as a boundary condition it can't ignore. Here's the connection to the shield above our heads. The outer core's dynamo runs on convection. Cool the core harder from above in one place, and flow speeds up there. Insulate it in another place, and flow slows. The geodynamo hates that kind of patchwork. Simulations that impose heterogeneous heat flux, hot caps that slow cooling, cool caps that yank heat out, show the flow reorganizing into jets and eddies that prefer certain longitudes. In those models, the hot cap roughly under Africa seeds weak and reversed flux patches in the outer core. When those patches reach the surface, you see them as depressed intensity and local polarity flips in the South Atlantic neighborhood, the same sore spot our satellites keep reporting. It's heat hacking. The blobs don't make magnetism, but they steer it by reshaping the heat map the core responds to. That's not just a pretty theory. The geometry lines up in ways that are hard to ignore. The African blob's footprint overlaps the long-lived weak region that shows up in archaeomagnetic reconstructions and the modern South Atlantic Anomaly. In swarm era maps, a second minimum southwest of Africa deepened faster, starting in the early 2020s, tightening the overlap with the African pile's complicated rim where ULVZs are common. If those ULVZs are iron-rich or partially molten, they'd act like localized insulators and possibly better electrical conductors. Better conduction means stronger electromagnetic coupling right at the boundary, another way to nudge flow and shear in the liquid iron above. Meanwhile, the Pacific blob tells a different story at the surface. It underlies plume highways and hotspot chains. But today, it doesn't host an SAA-style train wreck. That's a reminder. The mantle's fingerprint is a bias, not a destiny. The inner core's growth, compositional convection, and the core's own internal rhythms share control. Still, when modelers include both blobs and high-resolution dynamos, familiar features emerge. Westward drift of magnetic flux under the equatorial Atlantic, long-term intensity contrasts, and preferred birth zones for reverse patches. Add realistic boundary lumps, and the field looks more like the one we measure. Time is another clue. Tectonic reconstructions and hotspot tracks suggest the blobs have held roughly the same longitudes for hundreds of millions of years. If the boundary forcing is stable over that kind of time, the geodynamo inherits a memory. It still wanders and sometimes collapses into excursions, but it tends to form weak patches where the boundary keeps whispering. Here. That's why Africa keeps showing up in rock records when the field stumbles. Today's bifurcated anomaly might just be the latest pulse in a long conversation between the core and a stubborn chunk of mantle. There's a subtle wildcard at the rims. If ULVZs are metallic or partially molten, they can change both thermal insulation and electromagnetic drag at the core's roof. A small change in drag can alter the speed and position of shear jets in the outer core. Satellite inversions already reveal narrow westward jets beneath the equatorial Atlantic. If a reverse patch drifts into one, shear can stretch it into something the surface feels as a deeper, wider weak spot. That's a plausible path to the second lobe southwest of Africa, getting nastier faster. So the blobs aren't monsters, they're landmarks. Deep, dense, long-lived, and they tilt the table the geodynamo rolls on. Under Africa, the tilt favors weak, messy fields at the surface. That's the practical headline. If you fly satellites, schedule polar routes, or manage a grid on conductive crust, this deep structure is part of your weather now. The core is sensitive, the boundary is lumpy, and the African blob sits under the softest spot on our shield. The dynamo, how a planet makes a magnetic field. Follow the heat down past the blobs and you hit the engine room, a globe of liquid metal, 2,000 kilometers thick, circling a solid inner core like a storm around an island. The outer core is iron alloy under crushing pressure and fierce heat, but it flows. Motion is the point. When a conductive fluid moves through an existing magnetic field, it stretches field lines. That field, in turn, induces currents that feed back on the flow. That loop is the geodynamo. It's not a neat motor, it's turbulence with a memory. Two kinds of buoyancy keep it churning. Thermal buoyancy comes from the core losing heat into the mantle. Compositional buoyancy comes from inner core growth. As iron freezes onto the inner core, it releases latent heat and rejects light elements, like silicon, oxygen, or sulfur, into the outer core. Hotter, lighter fluid rises. Cooler, heavier fluid sinks. Add Earth's rotation and you get Coriolis forces that organize the chaos into helical columns, roughly aligned with the spin axis. Those columns wind magnetic field lines into a global pattern that, on average, looks like a tilted bar magnet. On average, is doing a lot of work, the system is sensitive, change the boundary conditions a little, cool faster beneath a cold patch of mantle, or insulate beneath a hot, chemically odd patch like the African LLSVP, and the flow reorganizes a lot. Conductivity is high, so field lines don't just snap. They slide, twist, and reconnect where the flow insists. That's why small nudges at the core mantle boundary can seed reversed flux patches in the outer core. Those patches are local regions where field lines thread the wrong way, and when they reach the surface, they look like the weak spots satellites dread over the South Atlantic. You can watch the engine's twitchiness from the ground. Over the past 2 centuries, observatories have measured about a 9 to 10% decline in the axial dipole moment, while energy sloshed into smaller scale features. In the satellite era, missions like SWARM have mapped narrow westward jets of magnetic flux beneath the equatorial Atlantic, suggesting shear zones inside the core that advect field structures like weather. And up north, the North Magnetic Pole sprinted toward Siberia at roughly 55 kilometers per year in recent decades, an outward sign that high-latitude flux lobes rebalance below the Arctic. Meanwhile, the inner core adds its own asymmetry. Seismic studies suggest hemispheres with different textures, possibly different ages, implying offbeat freezing rates. If one side of the inner core grows faster, it dumps more latent heat and light elements into the adjacent outer core, juicing convection there. From above, the blobs heat hack the boundary by redistributing heat flux. From below, the inner core stirs off-center. 2 metronomes beating out of sync in the same fluid make eddies, jets, and bursts the field can't ignore. What does that feel like at the surface? First, the dipole sags but doesn't vanish. At the same time, reverse patches bloom at preferred longitudes over hotter boundary regions and drift west with the core's jets. The map grows multipolar. Multiple poles tug on the auroral ovals, warp radiation belts, and change where charged particles dump into near-Earth space. Ground navigation can absorb slow drifts with updated models. Space systems are less forgiving. They're designed around expected flux, not surprise pits that deepen faster than a replacement cycle. The Dynamo remembers. Field lines thread through the fluid and couple distant regions, so a reversed patch can merge with a neighbor, get sheared into filaments, or fade if the flow starves it. That coupling makes prediction hard beyond a few years. You're forecasting turbulence with constraints, not a rigid magnet. Still, some patterns persist. Westward drift along the equator, long-lived low-intensity corridors keyed to boundary lumps, and decadal geomagnetic jerks when flow reorganizes abruptly. Fold in the blobs we met upstairs. Where the mantle above is hotter or compositionally distinct, heat leaks more slowly, convection slows, and reversed patches prefer to form. Where the mantle is cooler, heat drains faster, strengthening the field locally. The African LLSVP sits beneath the South Atlantic's weak corridor. Add narrow westward jets there, and you get today's bifurcation. 2 minima, the classic South Atlantic lobe and a deepening twin southwest of Africa, shaped by patch growth in shear. So the engine isn't failing. It's reconfiguring under uneven push and pull. In that reconfiguration, the tidy dipole shares power with noisy neighbors, and the sky stops behaving like the models we built a decade ago. That's the setup for everything that breaks next. Satellites, clocks, grids, and routes that don't expect a magnetic field with this many moving parts. How blobs break the field, from dipole to chaos. This is where the bar magnet frays into a crowd. A strong dipole keeps the radiation belts tidy and navigation simple. Break it into smaller poles, and the sky stops cooperating. The path from order to noise starts at the core mantle boundary, where the African blob's heat map leans on the dynamo like a thumb on a scale. Stakes first. When the dipole weakens and the map turns multipolar, satellites take more hits, timing gets jumpy, and storm hazards creep toward mid-latitudes. In daily life, that's rerouted flights, patchy GNSS, and power grids that feel storms they used to shrug off. Precision economics meets sloppy space weather. action down in the metal. Think of the outer core as fast lanes and eddies. Where the mantle above is cooler, the core dumps heat quickly and flow speeds up. Where it's hotter or compositionally odd, like above the African LLSVP, heat leaks slowly and flow slackens. Slow zones nurture reverse flux patches, islands where field lines point the wrong way. Satellites already map them under the South Atlantic. They drift west, merge, split, and sometimes bloom into surface weak spots. The SAA's two minima, one over the Atlantic, the other southwest of Africa, fit that script. Multiple patches seated above a hot boundary, sheared by westward jets along the equator. Here's the tipping logic. The global dipole can carry noise if reverse patches stay small and isolated. But as total energy in those patches grows, they start stealing the show. In high-resolution dynamo models that impose heterogeneous heat flux, patches born over the African blob lengthen in shear, hook together, and briefly outweigh the dipole's authority. That's an excursion signature. The dipole slumps, the map grows multipolar, and regional compasses grow moody without a planet-wide flip. If the patches lose their feed, the system snaps back. If they keep it, the slump can linger for centuries. Impact at the surface looks like 1,000 paper cuts. Radiation belts warp from neat donuts to lumpy, shifting bowls that dump particles into unexpected latitudes. Auroral ovals stretch and wander, regions under weak patches. South Atlantic, Southern Africa, downstream longitudes see more particle rain at lower altitudes. GAN-SS birds in medium orbits plow through thicker swells, racking up dose and glitches. Low Earth orbit imagers ride longer brownouts across both SAA lobes. Life expectancy bleeds away by statistics, not catastrophe. Meanwhile, jets matter. Satellite inversions resolve narrow westward flux jets beneath the equatorial Atlantic. When a reverse patch drifts into a jet, the shear can amplify it, stretching it into a surface depression wider and deeper than its seed. That's a clean path to the faster deepening lobe southwest of Africa reported in swarm-era maps since the early 2020s. Shred the patch instead, and fragments seed new minima downstream, lining up multiple weak spots along a longitude band. Exactly the kind of geometry operators now see. Why doesn't the Pacific blob deliver a mirror disaster today? Because boundary forcing is a bias, not a command. The inner core's asymmetry, compositional convection, and the core's internal rhythms set the rest of the stage. Right now, the beats line up to favor Africa. In a few centuries, the balance could swing. That uncertainty is honest. We know the mechanism, we see the patches, but forecasting their long-range dance is like calling eddies in a stormy river. Timescales split the risk. Core features evolve on years to decades. We've watched the North Magnetic Pole sprint at roughly 55 kilometers per year and the SAA bifurcate within a decade. Global flips are slower, centuries to millennia. The long blackout isn't lights out. It's years to lifetimes of weaker, patchier shielding that taxes tech every day. Design cycle, then cycle again, trying to keep up with a field that won't sit still. There's a quiet feedback at the boundary. If ultra-low velocity zones around the African blob are iron-rich or partially molten, they may alter electromagnetic coupling, as well as insulation. Stronger coupling can add or remove drag on flow near the core's roof. In a system, this sensitive, tiny drag changes can redirect jets a little, just enough to steer where reverse patches prefer to grow and how fast they deepen. That turns a seismic curiosity into an operations problem. So the rope bridge from dipole to chaos looks like this. Heterogeneous heat flux over Africa seeds reverse patches. Westward jets stretch and herd them. Patches merge into surface weak spots that warp belts and auroras. The dipole sags while multipolar features take the wheel. Satellites bruise, clocks jitter, and grids feel storms farther from the poles. You don't need a flip to live with consequences. You need a boundary that won't smooth out and an engine that listens to every nudge. And that's where we are. A sensitive dynamo under a lumpy lid already. Carving two pits into the South Atlantic corridor. The next question isn't will it reverse, it's which system blinks first as the map grows noisier. The tech kill chain, what goes dark first. Start in orbit because space bruises first. In low Earth orbit, every pass through the split South Atlantic corridor is now 2 rounds of particle hits. Error-correcting memory cleans most of it, until a spike slips past redundancy and a satellite reboots mid-slew. Star trackers see ghost constellations, imagers collect peppered frames, radiation counters climb, and mission control marks. Another forced blackout in the schedule. The math adds up quietly. More single event upsets per day, more anneal cycles, more dead pixels, and faster detector aging. Design lifetime shrink by statistics, not catastrophe. Climb to medium Earth orbit, where the timing constellations live. GNSS spacecraft already sit near the inner belt. A weaker, lumpy field lets the belt swell and slosh. Dose rates rise on certain arcs, especially where the second SAA lobe southwest of Africa bites hardest. So safe mode interruptions and clock resets creep upward. You can shield clocks and scrub memory, but you can't shield antennas. Signal quality wobbles under scintillation and particle rain. Operators either replace satellites faster or accept a constellation with more gaps and lower availability during storms. Neither choice is free. Now the ground feels it because timing is the scaffold. Financial trades, cellular handovers, grid synchrophasers, cloud databases, everything leans on nanosecond truth from space. In a multipolar thinning field, ionospheric irregularities wander. GNSS group delay spikes. Receivers lose lock more often. With enough bad minutes, distributed systems drift. A matching engine timestamps orders on diverging clocks. Audit trails fail to reconcile. And circuit breakers trip not because of price moves, but because the clock skew crossed the threshold. You layer in disciplined oscillators and chip-scale atomic clocks. They drift slowly, not wildly, but during a long space weather window, that drift shows up. Power grids are the next rung. Long conductors make great antennas for a sky that won't sit still. When a storm hits a slumped multipolar field, auroral boundaries sag, and quasi-DC electric fields thread into places that didn't used to light up. Geomagnetically induced currents sneak into transformer windings, pushing cores towards saturation. Protection schemes see a world that looks like a fault. Lines trip, reactive margins collapse, neighbors shoulder the load, and the stress cascades. Quebec's 1989 lesson plays out farther south on a day that wasn't supposed to be dangerous. Neutral blocking devices help. So does dynamic islanding and synthetic inertia. But aging fleets, long east-west lines on conductive crust, and thin spares turn a few bad hours into months of careful recovery if multiple high-voltage transformers overheat or crack. Aviation pays next in fuel and certainty. At cruise altitudes, dose stays manageable most days. But comms and navigation don't like a lumpy magnetosphere. Over the poles, HF fades. Over the South Atlantic corridor, SATCOM blinks when a relay bird hits the wrong lobe. And GNSS-based, required navigation performance approaches downgrade when ionospheric scintillation spikes. Dispatchers reroute flights to keep crew dose within limits and preserve comms, jogging around the southern lobe on active nights. 5 minutes here, 12 minutes there, that's real money across a fleet and real crew legality pressure on the wrong day. Maritime operations feel it in positioning and logistics. Big ships blend inertial and multi-constellation receivers, but dynamic positioning rigs and port cranes want centimeter-level truth. Under weak patches, multipath and scintillation rise, local differential corrections struggle, cranes slow to supervise mode, tugs fire up local beacons, schedules slip. It's not a collision, it's friction. Data centers are where timing's ripple becomes a wave. Cloud providers keep clusters coherent with consensus protocols that assume bounded delay and reliable time. During a storm window, GNSS degradations propagate as clock noise. Two-way fiber time links blunt it, but not everywhere. Holdover policies kick in, some shards fall back, quorum waffles. Writes pause to avoid split brain. Queues fill, retries multiply. Users see a spinner. It clears after the sky calms, but the postmortem shows the same route. One weak corridor aloft ballooned into a timing hole on the ground. Supply chains see it as ghost delays. A port under the southern lobe loses centimeter-level crane guidance for an hour. A rail yard slotting software drifts its clock and stalls handoffs. A cold storage facility flips to backup after a voltage sag. No headline, just throughput shaved from a system that budgets seconds. Insurance moves money around all of this. Underwriters reprice satellite hull and component. Coverage based on dose histories through both SAA lobes, discount designs with better total ionizing dose margins, and demand more on orbit spares. Grid insurers model geomagnetically induced current exposure with updated auroral maps and ask where neutral blockers are actually installed. When answers look thin, deductibles rise. Governments absorb tail risks when the market steps back, usually after one ugly season. The human rhythm runs underneath. A line worker hears a transformer sing and calls a controlled shed before the core bakes. A pilot crossing the South Atlantic sees SATCOM blink, checks HF, and flies the contingency route they drilled. A substation tech watches synchrophaser clocks drift and verifies fiber time took over. A farmer loses centimeter guidance for an hour, slows the pass, and files a warranty claim on a receiver the co-op will swap next week. None of it sounds like catastrophe. Together, it's a tax on precision. This is the chain in order. Space degrades first, single event upsets, dose, safe mode scars. Timing stumbles next, the heartbeat that makes distant machines act like one. Grids feel storms in new latitudes, with rare but brutal equipment losses when protection misreads a saturated core. Aviation and maritime adapt, but pay and fuel, delays, and training. Data integrity wobbles at the edges, then in the core when clocks disagree too long. Insurance prices the pain a year ahead of policy. And every redesign race runs against a field that keeps moving the goalposts. Not with a flip, but with a slow, relentless lean. Evidence from storms. Carrington to now. To see the ceiling, look up. In late August 1859, telegraph operators felt shocks leap from their keys. Paper smoldered. Auroras smeared across Cuba and Hawaii. Richard Carrington sketched a flash on the sun hours before the disturbance hit. We didn't have satellites, grids, or GNSS. The storm still broke things. Now place that same energy on today's lumpy field, with a split South Atlantic corridor and a dipole that sagged since the 1800s. The punch doesn't just land, it finds the soft tissue. Jump to March 1989. The sun coughed a coronal mass ejection that threaded north-facing lines into Quebec. 90 seconds after the storm peak, the grid folded. Geomagnetically induced currents drove transformers toward saturation. Protection misread the world and tripped. It wasn't global. It was a clean lesson. Long metal is an antenna, and storm energy turns into DC you never asked for. Utilities added procedures, a little hardware, and then budgets moved on. October 2003, the Halloween storms arrived like a rehearsal for a digital era. Satellites ducked into safe mode. GNSS accuracy wobbled. Airlines jogged polar routes. Aurora bloomed over the U.S. South. It still wasn't Carrington class, but it showed how a mid-range storm creates expensive noise when timing underpins everything. Now layer today's geometry. 2 SAA minima by 2024 to 2025. One southwest of Africa deepening faster since the early 2020s. Westward jets under the equatorial Atlantic, and the North Magnetic Pole's recent sprint toward Siberia at roughly 55 kilometers per year. Those alignments shape where energy couples in. Then the near miss. In July 2012, a Carrington-flavored CME crossed Earth's orbit a few days late. If timing had shifted, we'd have learned the hard way how a weakened, multipolar field warps the magnetosphere. Under a strong dipole, auroral ovals expand in predictable belts. Under a slumped, lumpy field, the ovals meander. Coupling strengthens in regions that aren't trained for it. The South Atlantic corridor becomes a low-altitude funnel, dumping particles into orbits we depend on for timing and imaging. Recent volleys hint at the choreography. In September 2017, X-class flares and fast CMEs rattled HF comms and degraded GNSS sporadically. Operators absorbed it. The SAA's bifurcation hadn't sharpened yet, and the southern lobe wasn't as deep. Today's swarm-era maps tell a tighter story. Risk clusters along longitudes where reverse patches and jets overlap. The Atlantic, Western Africa, and downstream arcs where satellites cut through the bowls twice per orbit. Now run the cascade when a big storm hits this board. Up high, satellites plow through swollen asymmetric belts. Single event upset spike. Star trackers lose lock. Imagers pepper with hits. Clock disciplining routines stretch. A few birds ride out prolonged safe modes. Constellation availability dips exactly when the ground needs clean time. On Earth, GNSS receivers see group delay and scintillation surge. Cellular handovers get sloppy. Exchange engines widen their guard bands. Some halt rather than risk split brain ledgers. Meanwhile, long lines feel fields where maps said unlikely. Mid-latitude grids on conductive crust, northern Europe, the northern US, South Africa, See JIT creep into transformer windings. Core is heat. Protective relays, tuned for a normal day, misjudge saturation. A few trips here, a few misoperations there, and the load migrates to neighbors already stressed by the same storm. Reactive margins narrow. In the wrong topology, a voltage sag cascades before operators can island. Aviation adds friction. Dispatchers reroute to preserve HF over the poles and jog around the southern lobe on active nights. Crew dose stays within limits, but SATCOM links drop when a relay crosses the deeper African side minimum. Required navigation performance approaches degrade, hold stack. Ports feel ghost delays when crane guidance loses centimeter truth under scintillation and switches to supervised mode. It's not a headline, it's throughput shaved at every link. There's an honest unknown. How close are we to the slump that turns a bad storm into a structural reset? We track the Dipole's decline, the SAA's bifurcation and deepening southwest of Africa, westward drift, and the pole sprint's tempo. The physics of storms hasn't changed. The board they play on has, and every year, the weak windows widen. The odds tilt a little more toward a day when luck runs out. The clock, field strength, drift, and the inner core. Clocks run the story because they set budgets, lifetimes, and routes. Since the mid-1800s, observatories have watched Earth's axial dipole fade by roughly 9 to 10%. Start with the big hand, strength. That's averaged across the globe. Locally, the changes bite harder. Over the South Atlantic, intensity contours sag, spread, then split. That's the map operators use to decide when to shut instruments, when to scrub memory, and when to accept the scar of a data hole. The dipole is the background hum. Regional slumps set the pace of pain. The second hand is drift. Magnetic features, especially near the equator, tend to slide westward drift at a few tenths of a degree per year. Satellite inversions trace narrow westward jets under the equatorial Atlantic conveyor belts carrying flux structures towards South America and Southern Africa. That's not trivia, it's logistics. Drift is how a weak patch you thought you understood ends up above your new ground station or your favorite orbit arc earlier than planned. Insurers know it. Mission planners who bet on yesterday's map eat the overrun. Up north, the minute hand can sprint. In recent decades, the North Magnetic Pole raced towards Siberia at roughly 55 kilometers per year. That dash isn't a surface whim. It's a deep rebalance of high-latitude flux lobes. Surveyors pushed emergency updates to the World Magnetic Model because apps, compasses, and runway headings slipped out of tolerance. It was a public glimpse of a private truth. The core can reorganize fast enough to break your maintenance calendar. The South Atlantic's timing is harsher. Between 2014 and 2025, swarm-era reconstructions show the anomaly expanding, while a lobe southwest of Africa weakened faster, starting in the early 2020s. That acceleration is a deadline hidden in a contour. GNSS birds rack up extra dose on that arc. Imagers spend more minutes blind, replacement cycles compress. If your shielding was sized to 2014, you're already behind. Under the hand sits a movement we can't open, so we infer it from waves and fields. The inner core grows as iron crystallizes onto its surface. Freezing releases latent heat and rejects light elements into the outer core, fuel for convection. If growth were even, timing would be kinder. Seismic anisotropy says it isn't. One hemisphere looks younger and texturally different than the other, hinting that freezing runs faster on one side. Offbeat growth is a metronome from below, adding asymmetry to the outer core's flow, while the blobs bias heat loss from above. Two metronomes beating out of sync matter because the geodynamo is sensitive. Heterogeneous boundary heat flux slows convection beneath hot, chemically odd patches like the African LLSVP. Faster inner core growth on one side injects buoyancy unevenly. When those beats line up over Africa, reverse flux patches above the core-mantle boundary grow faster and live longer. At the surface, the SAA's southern lobe deepens. The split sharpens. Satellite operators stop pretending the corridor is just one bump. How do we time the slope ahead? Watch 3 dials. First, dipole decay. If the global moment starts dropping faster than the long, lazy trend, the background gets louder. Second, reverse patch growth and westward drift beneath the South Atlantic. If patches merge and spread, expect deeper shielding holes and tighter avoidance windows. Third, the pole sprint's tempo. A sudden slow, stop, or veer means the Arctic flux balance has shifted again, with knock-on changes to high-latitude coupling and mid-latitude induction maps. There's a fourth dial we barely resolve: inner core rotation relative to the mantle. Some seismic studies suggest decade-scale changes, speed-ups, slowdowns, even reversals in relative drift. If real, that's another gear modulating secular variation. It won't flip the field on its own, but it can alter cadence. The difference between a manageable wobble and a jerk that forces a model update a year early and catches routes, surveys, and drilling plans off guard. Uncertainty isn't an excuse to wait. Confidence bands are widest in deep time and narrow in the satellite era. We're sure the dipole has declined since the 19th century. We're sure the South Atlantic weakened and clearly bifurcated into two distinct minima by 2024 to 2025, based on ESA swarm era analyses. We're sure the North Magnetic Pole sprint happened. We're less sure whether the next 100 years bring a steady sag or a sharp excursion. The risk window most experts see is decadal. More multipolar noise, deeper regional minima, faster map changes than design cycles like. So adaptation runs on this clock. Constellations precess away from the deepening southern lobe before dose models demand it. Grids stage neutral blockers where westward drift will move induction risk, not where it lived last decade. Airports and shipping lanes under the African side minimum practice degraded modes as routine. Data centers install fiber time now, not after a bad storm turns holdover into hours. You don't wait for a bell, you watch the hands. The field sets the tempo. We decide whether our systems can keep time when the drummer speeds up. The they factor: agencies, labs, and quiet panic. While the field twitches, the people paid to notice move without headlines. ESA's swarm team quietly turns 11 years of orbits into a map that shows the South Atlantic Anomaly, splitting cleanly by 2024 to 2025 into two distinct minima, with the lobe southwest of Africa weakening faster since the early 2020s. They publish, update the models, and send a nudge to mission planners. Assume two minima, not one. NOAA's Space Weather Prediction Center watches the sun's temper and prepositions alerts to grids, airlines, and satellite operators who don't want surprises. The US and UK push World Magnetic Model updates sooner when the North Magnetic Pole sprint towards Siberia throws runways and survey software off. Inside space agencies, SAA crossing isn't a scare line, it's a budget line. Radiation-hardened parts cost mass and money. An extra millimeter of aluminum around a detector means one less instrument, one less camera, one less customer deliverable. Procurement teams compare dose maps from swarm-era reconstructions against their constellation geometries and pick the least bad trade. If your medium Earth orbit arcs cut through the deeper African side minimum more often, you buy more shielding and accept shorter design life. You also buy spares. Quietly. Defense treats timing as infrastructure. GNSS is a backbone, not an app. Classified backups exist, but multipolar noise still smears signal quality. The question inside certain rooms is blunt. During a severe storm on a slumped field, how long can we operate with degraded time? That question doesn't make a press release. It shows up as funding for chip-scale atomic clocks on platforms, fiber time to key nodes, and orbit diversification that avoids the SAA's hungriest lanes. Grids learn from 1989, 2003, and 100 smaller jolts. NERC writes guidance for geomagnetically induced current monitoring, transformer thermal limits, and operational playbooks. Some utilities install neutral blocking devices at substations aligned with crustal conductors, where induction will be worst when auroral boundaries sag. Others defer. The SAA's bifurcation isn't their daily vocabulary, but the consequence is more frequent mid-latitude coupling as the dipole sags. NOAA briefings land in control rooms with suggested posture changes. Staff up, stage mobile generation, prepare to island if reactive margins erode. The best operators drill it until it's muscle memory. Insurers are the quiet hand on the tiller. Underwriters parse dose histories through both SAA lobes and price satellite hull insurance accordingly. If your birds cross the deeper African side minimum too often, premiums rise unless you prove higher total ionizing dose tolerance, better error correction, and on-orbit spares. Grid insurers run black box GIC models with updated geomagnetic maps and ask for transformer inventories, neutral blockers, and spare logistics. If answers wobble, deductibles jump. Reinsurers widen exclusions after one bad season. Governments absorb tail risk when markets blink. In labs, the arguments sharpen without theatrics. Dynamo modelers show that heterogeneous core-mantle heat flux, the heat hacking pushed by the African LLSVP, nucleates reverse flux patches under the South Atlantic, consistent with the observed 2024 to 2025 bifurcation. Seismologists refine blob maps with new earthquake datasets and pin down ultra-low velocity zones along the African rim that likely tweak boundary insulation and electromagnetic coupling. Paleomagnetists bring lava flows, baked clays, and tree rings, showing that the South Atlantic corridor has been a frequent soft spot and that the Lachamp excursion, framed by some as the Adams event around 41,000 years ago, came with shielding collapse and atmospheric chemistry shifts. The Neanderthal link stays in the proposed debated folder. That nuance matters. The stakes don't need exaggeration. Mission control translates nuance into checklists. SAA twin-lobe blackout becomes a scheduled gap on instruments. Memory scrubbing cadence tightens. Attitude solutions get second sensors because star trackers can't be trusted through particle rain. Flight dynamics teams tweak inclinations a hair to shave time in the deeper lobe without burning a mission. For timing constellations, clock redundancy and radiation hardening get prioritized over payload. The phrase design life variance due to bifurcation starts appearing in review boards. Airline dispatch offices add a column to the morning briefing, southern lobe status. When indices rise and the lobe looks hungry, polar routes jog. South Atlantic crossings get small offsets to preserve SATCOM windows. Dose forecasts become routine, not exceptional. Port authorities south of Africa add a degraded mode playbook. If centimeter-level guidance drifts, cranes slow to supervised operation, tugs switch to local beacons, and schedules flex. It's friction by policy, not by panic. There are gaps everyone knows. High-voltage transformer spares are still thin relative to a multi-region event. E-Loran trials exist, but national low-frequency timing backbones lag. Many constellations still fly heritage part size to 2014 maps, not 2025 split. Those gaps don't make front pages. They make risk registers, budget asks, and eventually, line items. Call it quiet urgency. Agencies avoid the word collapse and talk about secular variation. Operators bake fixes into upgrades, not warnings. Insurers change prices before politicians change laws. The pattern underneath is simple. Assume a weaker, messier field for longer. Harden the vulnerable links. Diversify time. Practice degraded modes. Preposition spares. The story we've told in rocks and models is already guiding purchase orders and flight plans. The field will keep drifting. The people managing risk are moving first. Building the shield. Mitigation playbook. We don't get to smooth the core, so we learn its rhythm and build around it. Think engineering judo. Redirect the force instead of taking it head on. Start above the atmosphere. Operators harden what they can't dodge. Radiation-tolerant processors, triple modular redundancy, aggressive memory scrubbing, and detectors that duty cycle through the 2 SAA pits. Constellations shift planes or tweak inclinations to shave minutes inside the lobe southwest of Africa. For medium Earth orbit timing fleets, shielding is sized to the worst-case lobe, not the average. Design lives shortened by choice, with faster manufacturing and more on-orbit spares to absorb the bifurcation's extra dose. A few teams diversify architecture. Higher inclination relays and lunar-adjacent links route data and time around the bowls entirely. It's mass and money. It's cheaper than losing years to a map that moved. You also fly smarter. Past scheduling avoids the deepest minima during sensitive operations. Star trackers cross-check with sun sensors and gyros through particle rain. Onboard anomaly detectors learn the corridor's signature and preemptively throttle instruments before watchdogs trip. Ground segment plans for blind arcs, autonomous scripts, queue commands, verify after the corridor, and flag anything that smells like a single event latch-up. On Earth, long metal needs a firewall. Neutral blocking devices insert capacitors in transformer neutrals to keep quasi-DC geomagnetically induced currents out of windings. You don't carpet bomb. You place them where crustal conductivity and line geometry focus induction when auroral boundaries sag long east-west corridors, coastal grids, and high-latitude tie lines. Operators add GIC monitors to substation neutrals and feed live readings into thermal models that predict core heating in real time. When numbers climb, control rooms shift posture, boost reactive support, reconfigure flows, and island fast. Synthetic inertia from batteries and inverters buys seconds when frequency wobbles. High voltage direct current links act like circuit breakers between regions, quarantining trouble when neighbors stumble. Timing gets belts and suspenders. Multi-band, multi-constellation receivers ride out ionospheric mess better, but they still share the sky. So you add terrestrial time, E-Loran. Those low-frequency towers your grandparents forgot, cuts through scintillation and doesn't care whether your rural oval wandered tonight. Two-way time transfer over fiber stitches, data centers, and grid control rooms to stable references with nanosecond-level accountability. At the edge, chip-scale atomic clocks sit in base stations, substations, and exchanges, disciplined to sky most days and drifting slowly when GNSS stutters. The orchestration matters. Holdover policies that degrade gracefully, alerts when clocks diverge, and clean rejoin, so ledgers don't split into two truths. Aviation turns degraded modes into routine. Dispatchers brief southern lobe status alongside turbulence and winds. When indices rise, polar routes jog, and South Atlantic crossings get small offsets to preserve SATCOM. Crews carry live dose reads instead of monthly averages. Navigation won't be single-threaded. Inertial plus multi-constellation, GNSS, augmented by dual-frequency ground-based augmentation where available, with terrain matching near airports if satellites sulk. Regulators help by certifying required navigation performance paths that assume periodic GNSS loss without turning back the clock on safety. At sea, resilience hides in boredom. Dynamic positioning rigs add star trackers or optical horizon sensors. Port cranes practice supervised mode when centimeter-level guidance wobbles under scintillation. Tugs keep local beacons hot. Harbor authorities run drills for hour-long timing degradations. Slow, don't stop. Grids and telecoms practice the bad day. Utilities script storm posture, staff up, lower power transfers on vulnerable tie lines, pre-stage mobile generation, and set thresholds for islanding before. Voltage sags cascade. They test under load, not in slide decks. Carriers deploy fiber time to regional exchanges, teach radios to fall back to holdover cleanly, and widen handover tolerances during storm watches. After one ugly afternoon, a city learns to shed elective load while keeping hospitals, water, and communications steady. Cloud and finance do the same for truth. Data centers install redundant fiber time feeds, secondary sky receivers, and oven-controlled or atomic clocks. Consensus protocols get tuned for delay tolerance. Fewer split brains when jitter spikes. Rejoin procedures, how two shards reconcile after hours apart, are tested with live traffic. Exchanges expand timing attestations. Every order stamped with local and network time plus uncertainty, so circuit breakers understand clock drift, not just price moves. Insurance pays for behavior change. Underwriters discount satellites with higher total ionizing dose tolerance, better error correction, and proven spares. They cut grid premiums where neutral blockers, GIC monitors, and spare transformer programs exist. Airports that install dual-frequency augmentation, backed by terrestrial time, pay less. Governments amplify the nudge. Fund a national E-Loran backbone, subsidize spare high-voltage transformer manufacturing, and require microgrid-ready wiring in critical facilities. It's not flashy, it's leverage. Communities build nets under nets. Microgrids stitch schools, clinics, and fire stations to solar and storage with controllers that don't panic at frequency wobbles. Emergency services drill loss of signal days, HF and VHF radios with hardened repeaters, deployable mesh for neighborhoods, and paper fallback for the few hours a year when clocks aren't friends. Farmers get co-op programs for inertial add-ons and training on degraded guidance profiles, trading a little speed for less rework. The through line is speed. The southern lobe won't wait for a budget cycle, so mitigation chases drift, not history. Constellations precess away from deepening pits before dose models force it. Utilities stage blockers and spares along the path westward drift will move induction risk. Airports and ports beneath the African side minimum make degraded modes muscle memory. Data centers pull fiber time now not after holdover hurts, We won't build a dome, we'll stitch a patchwork. Spacecraft that shrug off more hits, grids that flex, clocks that don't panic, and crews who know the drill when the sky gets loud. The field will keep leaning. Our shield is how lightly we bend when it does. Wildcards, primordial piles, sunken continents, and deep quakes. We've stayed cautious so far. Facts first, models second, but some clues at the core's edge hint the blobs may be stranger than hot piles. Start with composition. If the African and Pacific blobs aren't just warmer, but slightly enriched in iron or other dense components, they'd be heavier and more stable. That would lock their footprints in place longer, making their heat hacking of the core's boundary harder to shake, and biasing weak field tendencies above Africa across long stretches of time. Where would that extra density come from? Two suspects. One is recycled oceanic crust. Over hundreds of millions of years, plates subduct and drag basalt and eclogite into the mantle. Some of that slab graveyard likely sinks deep, pooling near the base because it's denser than surrounding rock. The other is primordial residue, material from Earth's violent formation that never fully mixed. If either or both fortify the blobs, you get thermochemical piles, hotter and compositionally distinct. Seismic tomography can't hand us a sample, but it does show slower shear speeds inside the blobs and ultra-low velocity zones at their rims that behave like thin puddles of partially molten, possibly iron-rich material. Those ULVZs are tiny compared to the blobs, but outsized in effect. A patch of partial melt insulates the core locally, changing how heat escapes into the mantle above. If it's iron-rich, it may also boost electrical conductivity near the boundary, tweaking electromagnetic coupling between core and mantle. In a dynamo, this sensitive, small shifts in insulation and coupling can nudge shear jets, guide where reverse patches prefer to form, and alter how fast weak spots deepen at the surface. That's a plausible way a seismic curiosity at the African rim translates into the faster deepening SAA lobe southwest of Africa. We see in swarm-era maps since the early 2020s. There's also the plume traffic. Blob rims are plume factories. Many mantle upwellings that feed hotspots like Hawaii and Réunion trace back to those margins. Plume production probably isn't steady. Pulses happen. When a rim lights up, it's a sign of changing heat flow at the boundary. It's tempting to ask if pulses in plume generation correlate with geomagnetic jerks, those abrupt changes in secular variation we detect every decade or so. A few studies whisper. Timing overlaps, but causation isn't proven. Still, both are signatures of reorganizing flow near the core's roof. The test will be tighter correlations and dynamo models that ingest time-variable boundary maps, not just static lumps. Another wildcard is motion. The blobs look long-lived in longitude, but they might not be perfectly fixed. Over tens to hundreds of millions of years, mantle circulation could herd them, fed by slab graveyards piling up along their flanks. If they drift slowly, the planet's preferred weak windows would migrate too. That could help explain why certain longitudes dominate reversal behavior in some eras and not others. Today, Africa holds the bias. In a different continental lineup, the Pacific might. Let's clear a few headlines. The blobs are not sunken continents. They're deep mantle features, not crust. ULVZs aren't lakes of pure iron. They're likely patches of partially molten iron-enriched silicate. And while the Adams event framing of the Lashkamp excursion suggests ozone loss and environmental stress around 41,000 years ago, the link to Neanderthal decline remains debated. The solid core of the story stands without embellishment. Deep structure biases the geodynamo. The South Atlantic sits above the most consequential bias today. There's one more speculative lever: boundary conductivity. If certain rim zones are more conductive, they could transmit electromagnetic torque from the core into the mantle more efficiently, adding or removing drag-on flow near the top of the liquid iron. Even a small change in drag alters where shear bands stabilize. Satellite inversions already reveal westward jets under the equatorial Atlantic. If conductivity variations steer those jets a hair, they steer patch growth a lot. So what are the wildcards bias? Not certainty, texture. The blobs likely mix heat and composition. ULVZs modulate insulation and coupling. Plume pulses hint the boundary breathes. Slow drift keeps the bias long-term but not eternal. Conductivity patches tweak the brakes. Each is a small lever. Together, they tilt the field toward long-lived weak corridors and sudden jerks, without promising a clean flip on human time. That's enough to matter for orbits, clocks, and grids. We don't need monsters in the deep. We need a boundary with character, and we've got one. Life in a long week field, a lived scenario. Year 5 of the slump feels like routine with sharper edges. In a ground station outside Windhoek, a timing operator watches the afternoon window when GNSS quality dips as the southern lobe breathes. Fiber time carries the load for 2 hours. At 17:12, the dashboard flags a holdover drift under a threshold they've memorized. No one panics. A script hands clocks back to the sky when the indices ease. It's a learned reflex, not drama. On orbit, a small Earth-imaging satellite prepares to cross the corridor. The payload toggles to a harden mode before the twin pits. Star trackers blend gyro bias until particles thin. The ops lead sips coffee, marks the blind arc, and mutters about dose budgets drifting faster than procurement. Ground will stitch the gap later. The replacement queue lengthened after insurers raised premiums for arcs that bite the lobe southwest of Africa. The schedule now includes a line item called SAA Twin Pass Cost. A decade in, budgets carry the field's fingerprints. A timing constellation adds mass for shielding, trims design life by choice, and buys more spares. A regulator greenlights a national ELOR and spine because jittered trades prove pricier than towers. Grid planners in South Africa and Brazil install neutral blockers along long east-west corridors where models say induction will spike as auroral boundaries sag. A crew drills islanding a district in 8 minutes. After the shift, a line worker shows a new hire. She goes of the hum a transformer makes when quasi-DC sneaks in. That's your early call, phone the shed. On a Sao Paulo to Cape Town run, the morning briefing lists space weather as a column, not a footnote. Indices elevated after local midnight. The southern lobe looks hungry. Dispatch adds 100 miles in 5 minutes to keep SATCOM windows intact and dose conservative. Over the corridor, the SATCOM blinks, HF holds, and the crew rides procedures they practiced. Passengers never know. The airline logs fuel costs under a code that didn't exist 10 years ago. Ports adjust with boredom. In Walvis Bay, cranes slow to supervised mode as scintillation nudges centimeter-level guidance off. Tugs flip on local beacons. A cargo planner slides 3 ships and updates gate times. No headlines, just friction. The port manager's weekly call mentions the pattern. The southern lobe bites harder near moonless nights after active days. They schedule the tight moves in calmer slots. A farmer in Kansas finishes rows after rain. Guidance throws an error as scintillation rises on a southern sky patch. The co-op's winter class taught a degraded profile. He shifts to it, loses a little speed, and skips rework. The receiver goes on a list for an inertial add-on paid through a county grant that mentions space weather without fuss. By year 20, mitigation feels baked in. Cloud providers anchor data centers with 2-way fiber time, secondary sky receivers, and oven-controlled or atomic clocks. Consensus algorithms get tuned for jitter. Once a month, a storm stretches holdover into hours. A region sees spinners and recues. The postmortem doesn't say magnetosphere collapse, it says timing degraded gracefully and rejoined cleanly. Finance trades widen guard bands when space weather alerts go orange. An engine halts once a year for clock skew, not price, then comes back honest. A refinery on a coastal grid adds power electronics that ride harmonic swings. The nuisance trips that used to cascade into flares drop. Someone in accounting maps the capital expense against avoided downtime. The line labeled geomagnetic events shrinks quietly. A utility posts an ops video where a dispatcher walks through a storm posture. Reactive support up. Transfers down. Islanding thresholds set. Crews staged. Neutrals watched. The hummed lesson from 1989 and 2003 moved from lore to checklist. Human stories knotted together. A medevac crew over the Southern Atlantic hits a comms hole and flies the contingency route until the relay clears the deeper lobe. A radio amateur in Cape Town watches HF bands open strangely and runs a neighborhood net for 2 hours while cell towers jitter. A school in Luanda finishes a science fair on its microgrid while the city flickers. Parents complain once, then see the outage graph and stop asking why the battery room matters. By year 30, weather apps add a space tab with timing and grid risk as traffic lights. Airlines hire route meteorologists who think in particle rain and scintillation. Surveyors update headings faster when the world magnetic model rolls early. Port captains talk about lobe moods like tides. A new transformer plant in the Midlands stamps out units because waiting 2 years after a storm wasn't an option anymore. Students line up for classes in time transfer, power electronics, and space systems that don't assume a tidy dipole. Inequality shows. Wealthy grids harden first. Smaller systems take hits and recover slower. Regional compacts buy spare transformers. Neighbors share Eloran towers that stitch timing over borders. The map looks fairer after a good policy year and meaner after a bad storm. Decade 50. The southern geometry shifted again. The pole wandered on. Kids who grew up with alerts let their phones slide to ground time without noticing. Their planes take slightly longer paths some weeks. Their cities island without fuss. Their bills include a slice for blockers, towers, and spares. They don't know the African blob's name. They know the light stayed on. Lessons from past excursions. The clues aren't in models first. They're in stone diaries. Lava cools and locks tiny iron grains into alignment with the field of the day. Layer flows across a hillside, and you get a flip book of direction and strength. Sediments do a slower version, stacking compass needles over centuries. Trees and ice add the sky's voice. Cosmogenic isotopes, like beryllium-10 and carbon-14, jump when cosmic rays surge through a weaker shield. Put them together, and you see a planet that sometimes stumbles, then finds its footing. The headline stumble is the Lashkamp excursion, about 41,000 years ago. It wasn't a clean, global, permanent flip. It was a deep slump with a brief reversal and a recovery. Field intensity crashed to a small fraction of today's value. Ice cores and ancient kauri trees record a sharp radiocarbon spike, proof the atmosphere was bombarded more intensely. In that window, auroras probably wandered far from the poles, and the upper atmosphere's chemistry shifted. Less ozone, more oddities in winds and temperature layers. There's a bolder framing you'll hear, the Adams event. It stitches the Lashkamp slump to environmental stress. Ozone thinning, regional climate nudges, even a proposed overlap with Neanderthal decline. It's a striking alignment, not a verdict. The timing overlaps, causation is debated. What's solid is simpler and still heavy. When the dipole slumps hard, radiation climbs, auroral boundaries swell, and the sky grows unruly for centuries. Our ancestors had caves and patience. We have satellites and clocks. Lashkamp isn't a loner. Around 34,500 years ago, the Mono Lake excursion wrote a shorter, shallower version of chaos. Near 64,000 years ago, another wobble flickered in the North Atlantic records. In some lava sequences, directions whip tens of degrees between flows laid down a few years apart. That's the core reconfiguring on human timescales. The globe takes centuries to swing. Regions can snap in seasons. It matches what satellites now watch in miniature. Reversed patches, birthing, drifting, and splitting like weather. Stretch the timescale to seafloor stripes, and you see the long rhythm. As magma froze along mid-ocean ridges, it recorded polarity like barcodes. Reversals aren't periodic. They cluster, then pause. Between full flips, live excursions. Skip beats that never resolve into a permanent switch. The pattern's geography matters. Paleomagnetic maps show weak corridors recurring at certain longitudes. Africa shows up often. That's the same bias today's deep structure suggests. A lumpy core-mantle boundary, nudging the geodynamo into repeatable trouble spots. Closer to our timeline, archaeomagnetic records add personal scale. Fired pottery, kilns, and slag remember intensity when they cooled. The Levant shows a long intensity high in the Iron Age, while the South Atlantic trends weak. Over the last 3 millennia, reconstructions sketched non-dipole features pulsing and drifting, but they cluster, and the South Atlantic corridor has history. Today's bifurcated anomaly sits on old ground. What did past slumps feel like on Earth? Models and proxies point to expanded auroras, altered UV at the surface due to ozone thinning, and small shifts in circulation. Not a global fire, a persistent mood. In a Lashbeer-grade world today, substorms would light up at latitudes that don't practice for them. The radiation belts would dump into orbits we rely on daily. Timing would jitter more often. Grids would see geomagnetically induced currents in places that thought they were safe. The physics rhymes. The stakes don't. There's a comfort tucked in the rock record. The field can wander far and still come back. Excursions end. Life adapts. The caution is timing. Regional collapses can arrive faster than we rotate a design cycle. The lesson isn't fatalism, it's agency. The deep engine will slip into its next skipped beat whenever it chooses. Our job is to make sure a century of flicker doesn't feel like collapse. The rocks are honest. Weak windows open first over familiar longitudes. We already live above one. The verdict: collapse, flip, or long slog. So which future are we living toward? A sudden collapse, a clean flip, or a long, messy slump? The facts point to the slog. What we see right now isn't a bar magnet dying. It's the dipole sharing power with loud neighbors. Reverse flux patches are growing under the south. Atlantic and drifting west. The anomaly is split into two minima by 2024 to 2025, with the lobe southwest of Africa deepening faster since the early 2020s. The North Magnetic Pole's sprint, about 55 kilometers per year towards Siberia, confirms that high-latitude flux rebalanced. None of that matches an imminent global reversal signature. It does match excursion physics, a weakened multipolar map that lingers. Add the boundary bias. The African LLSVP's heat hacking doesn't flip the planet by itself. It seeds weak zones and sustains them. High-resolution Dynamo models that impose heterogeneous heat flux reproduce the reverse patches we're watching. That makes an excursion more likely than a tidy flip on a human schedule. Timing seals it. Full reversals unfold over centuries to millennia. Excursions can rise in decades and stretch for centuries. Our clocks. The dipole's roughly 9 to 10% decline since the mid-80s, SAA bifurcation by 2024 to 2025, westward drift, and that pole sprint are moving on decadal beats. That cadence favors a protracted weak field era with periodic deep slumps. It also fits the practical pattern. Tech failing in clusters, redesign racing the map, insurers pricing the truth a year ahead. Wildcards don't change the direction. Intercore asymmetry may modulate cadence. ULVZs at the African rim probably tweak insulation and coupling. Past excursions, last shot foremost, show how far the field can sag without a permanent flip. The Adams event framing adds environmental stress. The Neanderthal link remains debated. We don't need it to set stakes. So the verdict: expect regional collapses, not a planet-wide flip on any policy horizon. Expect more multipolar noise riding a sagging dipole, with weak windows clustering over Africa and downstream longitudes. Watch three triggers: a steepening in dipole decline, merging reverse patches beneath the South Atlantic, and a change in the pole sprint's tempo. If two move together, budgets move now. Mitigation shifts outcomes. Harden timing. Block GIC. Redesign orbits to shave the deeper southern lobe. Stock transformer spares. Drill degraded modes. We won't steer the core. We can blunt how much of its mood reaches us. This era isn't lights out. It's a century of flicker that punishes fragile design and rewards resilience. If you want to see how one storm could force global grid rules to change overnight, watch the modern Carrington scenario next. Subscribe for more grounded, unnerving science, and share this with someone who thinks GPS timing can't fail. They'll thank you the first time the sky gets loud.